I'd like to briefly recap what I taught last lecture. So, we were talking about electrochemical machining, some basics and fundamentals. As I would like to just mention here that it is a process where the tool is made the negative electrode, the cathode, and the workpiece is made the anode. And then the choice of electrolyte is done in a manner so that whatever dissolves off the anode goes as a precipitate into the solution, and it is circulated so that there is no deposition back on the tool cathode, and this way the whole process is used or is made amenable to machining of materials. So, we also did some estimation of material removal rate, and we studied Faraday's law in the process, and we were yet to sort of predict what amount of material per unit time may be removed by this process when we started looking at the very first important thing in electrochemistry or in any electrochemical operation, which is the ion transport equation. Okay. So, as a part of that equation, if you may remember, we had actually tried to study what the impact of a positive ion, a central ion of interest would be in assembling its negative charge atmosphere around it, and we studied that what the potential would be at a function at a point A. If we assume that at an infinite distance there is a charge number density represented by n plus 0 and n minus 0, and near this at A it is n plus and n minus. So, and we try to find out the potential arising out of this situation, and the xi was represented as A square of k by 4 pi dielectric constant d times of e to the power of minus kr by r. Okay. So, that is how xi, a potential at point A, would be as a function of r. So, for electron neutrality, the total negative charge assuming the central ion to be positive, of the atmosphere about a given ion as of the atmosphere, and the charge of the central ion be plus z I epsilon, thereby meaning that the atmosphere would have a charge of minus ZIE. So, we can assume that, let us say, if you have a central ion here and you are looking at some distance r from this ion, okay, as if there is a shell of thickness dr around this distance r, and then you say that there is a distance a, or the ion size parameter, at which the the ion kind of gets truncated. So, this is the radius of the ion. So, we can assume that the total charge which is available because of this positive central ion of interest can be represented as the volume element dV here times of the volume charge density at this point. So, rho times of dV, right, and this varies between, let us say, some distance a all the way to when r goes to infinity, okay, and that can be made equivalent to the charge minus ZIE, the total charge in the atmosphere around this central ion of interest. So, dV, of course, as you know, is nothing but 4 pi r square dr. Okay, this d by dr of sort of 4 by 3 pi r cube. So that is how this volume element or this shell would be around this whole central charge of interest. And so therefore, the volume integral a to infinity of 4 pi r square times of rho charge density, which has been represented earlier. You know that rho has been represented earlier as a k square by 4 pi d e to the power of minus k r by r. Okay. So this charge here a times of square of k by 4 pi d times of e to the power of minus k r by r times of dr. Okay. So that is equal to minus z I epsilon, and therefore, we can just simplify this equation. So let this be equation 1. So we can simplify this equation further to obtain a square of k d by times of integral 0 to a 4 or r times of e to the power of minus k r equals to z I e. Okay. So because there is a minus term which comes from the potential, the charge density. So that is the final integral that we have to solve. So we have to integrate this expression by parts. Okay, as we know that the formula of integration by parts is a to b f x g dash x dx equals f x g x between the same limits minus integral a to b of f dash x times of g x times of dx. Okay. And here, as we know that f x equal to r and g x or g dash x, if we assume it as e to the power of minus k r, thereby meaning that g x can be equal to minus e to the power of minus k r by r. Okay. So we can actually write this whole expression by parts as integral a to infinity r e to the power of minus k r, okay, as minus r e to the power of minus k r by k varying between a and infinity, minus of e to the power of minus k r by square of k varying between a and infinity. Okay. And this therefore can be further represented as a e to the power of minus k a by k plus e to the power of minus k a by square of k, and so simultaneously we can have a square of k times of d times of e to the power of minus k a by k. Okay. Because we are just substituting this result into the equation formulated earlier here, okay, the equation 1. All right. So it has been just the same equation formulated earlier. So therefore, e to the power minus k by k times of square of k, okay, times of k a plus 1 equals z I e, or in other words, as you already know that the potential function xi is a e to the power of minus k r by r, and a from here can be found out as square of k goes away. So we are left with z I epsilon divided by d times of 1 plus K A e to the power of K A as A, and potential function xi can be represented as Z I epsilon d to the power of, or d times of 1 plus K A times of r times of e to the power of minus k or let us say plus k A minus r. Okay. So, that is how the potential function xi can be calculated as. So, I would like to now just sort of bring your attention to what would happen at the surface of the charge central ion, which is at a distance a from the center of the ion. So, we can assume that this influence or domain of the charge varies between r equal to 0 and a, although the charge is kind of super concentrated at the center of the ion. Okay. So, that is the concept of a point charge, that the charge is concentrated at a point, but then it can have a radius 0 to a. So, at a, the potential, because of the charge which is somewhere here or hidden here, can be represented as xi at r equal to a is Z I epsilon by d times of 1 plus K A times of A. Okay, r equal to a, and when you put r equal to a here, this exponential term goes away. So, this is equal to 0, sorry 1. So, therefore, that is how the potential at a point A on the surface of this point charge can be recorded as. We can further try to sort of split this into a partial fraction and try to have a look into what all components would go in formulating a potential at the point A. So, here let us say the xi therefore at r equal to a can be written down as Z I e by d times of 1 divided by a times of 1 plus K A, meaning thereby it can be Z I e by d times of 1 by a minus k by K A plus 1. Okay. And this is how it would happen when it is resolved into partial fractions. And we can represent this as Z I e by d A minus k times of Z I e by d times of 1 plus K A, and this can further be expressed as plus minus Z I epsilon by d A minus plus, depending on the value of the charge, K Z I epsilon by d times of 1 plus K A. Okay. So, just by the look of it, it appears as if this can be the effect of the central positive ion. Okay. And this component, because it is exactly the opposite of it, can be the effect of the charge atmosphere, which is principally negative charge. So, therefore, the potential contribution at the surface of the charge would come due to the ion itself and due to the atmosphere of the ion, and the equivalent radius of this ion atmosphere can be treated to be 1 plus K A by K. Okay. So, this is the, from this term here, this is the equivalent radius of the ion atmosphere, and this let this be called equation 2 here, okay. And this would be of some relevance, because we will try to utilize this in order to find out what is the potential of such a surface, which would get, which is nothing but an assemblage of the charges of one type with respect to the charges of other type, which is present lined up as the Helmholtz layer near the surface as a dual layer. Okay. So, this ion atmosphere would become very relevant in calculating the zeta potential of the surface at that stage. But you do understand that the contribution of the ion atmosphere onto the ion's surface also is of equal amount of significance and relevance in this particular illustration. So, let us now look at some of the very basic fundamentals of what happens when an electrode is dipped in a solution, which creates an assembly of the charges cut. So, let us now look into a slightly different aspect of the double layer, as I was mentioning before. Okay. So, how does the double layer get formulated? Let us say this is the electrode surface that we are looking at, and this zinc, and this is immersed in just a brine solution, NaCl plus H2O, salt water. Okay. And so, there is an automatic tendency of the zinc to formulate zinc ions. So, they would actually be ions of zinc which would come out in dissolved manner from the electrode, and there would be water molecules which would be immediately encircling the zinc, so called. Okay. So, this is the water molecule encircling the zinc, and that is how this whole orientation would be. So, each of the zinc atom is surrounded by a bunch of water molecules, and that is true for all the zinc atoms which are there in the solution. And correspondingly, there are negative ions which are there on the electrode side. So, there are positive ions in the solution and the negative ions in the electrode side. So, they should be equal and opposite if there is no external field that is influencing the system, because whatever number of zinc atoms are liberated as ions into the solution should have charge wise the similar amount of electrons on the electrode surface. So, what is important and worth here to mention is that there is a thin layer of water which would come between the positive charges and the ions, separating them from each other, and thus the zinc plus 2 cannot get deposited back onto the electrons, and this becomes electron rich, and there is a field which exists between the the first layer of zinc ions which are here, and this is known as the Helmholtz layer, and the layer of electrons which are on this other side here. So, there is an electrostatic interaction between the electrode charge and the solution charge, that is number one, and then ions from the solution may approach the electrode surface only so far as their inner solvation shells. So, solvation cell is this shell which is formulated because of the water molecules, okay, around the zinc plus 2 atom. So, as much as this solvation shell can allow, only that much distance the ion can have in proximity to the electrode charge, electronic charge which is on the electrode. So, the surface array of the ions is thus cushioned from the electrode surface by a monolayer of solvent. And the line drawn through the center of such ions at this distance of closest approach marks a boundary, and this is known as the outer Helmholtz plane, is indicated here. Okay. So, this is an assemblage of all the zinc plus 2 atoms hold on to a certain line, and the size of ions formulating the outer Helmholtz plane are larger, and the total number of ions needed to do a complete charge balance cannot all be fitted on this plane. So, obvious reasons that electron here in the electrode is a part of the electronic structure, much more densely packed in comparison to the ions which are in the solution, which are positive ions. And so, therefore, not one layer, but subsequently a set of layers would be needed for. So, for example, let us suppose this is the electrode surface, and you have negative charge assembly here in the electrode surface. So, the first set of Zn plus 2 ions would not be able to take care of the total electronic charge which has been emanated in this surface. This is, mind you, so it is a sort of atomically impregnated into the surface, these electrons, and these are full size ions in the solution. So, there has to be subsequent layers which would be responsible for whatever field escapes this first line of ions, okay. And then slowly the field gets neutralized and the ion layers get thinner and thinner as you go radially from the electrode into the solution. So, typically this layer in such a case is known as the first layer of charge, and so it is the Helmholtz layer, and this is demarcated by this outer Helmholtz plane. And this layer here, right here, okay, is sort of a diffuse layer of charges, and therefore, in electrochemistry mostly there is a Helmholtz layer and then there is a diffuse layer which has its own contribution in terms of capacitance. So, this is CH and this is CD. Okay. So, the capacitance of the Helmholtz layer is what generates because of this solvation shell of individual ions, separating the ions from getting back into the electrodes packed with electrons, and the diffuse layer which is there and formulated inside the solution. So, that is what the orientation here is. So, therefore, the remaining charges are all held, as you know, with increasing disorder in the outward direction into the solution, and this is known as the diffuse layer of charges. Okay. So, that is why double layer. So, you have one layer which is the Helmholtz layer and then another layer which is the diffuse layer of the charges. So, that is how in a nutshell the the whole electrode is oriented with reference to the solution. Okay. So, let us actually now look into how the potential zeta would vary with respect to distance from the electrode surface. So, if you plot the potential zeta with respect to x, okay, the distance into the solution, as you can see the potential varies linearly like this all the way up to this value here, which is actually, as I will later on tell you, the zeta potential of the surface. And then after that, the moment it crosses the outer Helmholtz plane, the potential starts varying of the diffuse layer in a different manner. It is not it's a non-linear behavior in this particular zone. So, we have to somehow be able to find out what this potential function is with respect to x. Okay. And as obviously as we have done before, at x equal to infinity, the potential function zeta is actually equal to, or xi is actually equal to 0. So, this calls for the solution of the Debye-Huckel theory in 3 dimensions, as we did just about few slides back in an ion solution, to a 1D case, right. A 1D is only the dimension of interest from the array of ions which are somewhere here, okay, on the electrode. So, this is the array of ions, and with respect to that array of ions, maybe we can consider this all focused on to a single place. Okay. With respect to this one, let us say central ion as an array available as an array format on the electrode, what is the distribution of the charge in the solution, and thereby the potential function would be recalled in that case. Okay. So, it is simply a one dimensional approximation of the Poisson's equation. We can just write d2 xi by del x2 is actually equal to square of k, okay, times of xi, as you already know from earlier equation. This square of k is basically the function which comes in terms of sigma ni zi square of epsilon by kt times of so on and so forth. Okay. So, that is what the k square term is here. Also, what is of interest and significance is that, as we found out last time, that with respect to the central ion, there is an effective radius of the ion atmosphere, and this effective radius was given by 1 plus Ka by k. In other words, it means it was 1 by k plus a. Okay. So, that was the radius of the effective surrounding ion atmosphere with respect to the central charge of interest. So, we will consider the similar value here and try to see what this function results in. So, by the theory of ion association, I would just like to just simply state it without really getting into the proof of it, but by the ion association theory, the value of 1 by k, okay, in the ion atmosphere comes out to be equal to the diffuse layer thickness let us call this thickness delta. Okay. And as you already know, square of k times I in this equation del 2 xi by del x2 is actually equal to minus 4 pi rho by d, right, where rho is the charge density at a particular point, d is the dielectric constant of the medium. That is how the Poisson's equation was initially illustrated. So, for this part of the equation, the simple solution for this part xi x comes out to be equal to the standard solution a e to the power of minus k x plus b e to the power of k x. That is how the standard solution to this problem would look like. And we again apply in the same manner the boundary conditions. So, we know that at x equal to infinity in this particular case, the potential at infinity is 0, meaning thereby that b automatically becomes 0, because otherwise at infinity this term is very large. The only way you can satisfy the solution is by assuming a very small b, negligible or 0. And simultaneously the xi x comes out to be equal to the potential function at point x comes out to be equal to a e to the power of minus k x. Okay. So, simultaneously again the rho, which is actually represented by minus square of k times of xi d by 4 pi, looking at these two parts of this equation, okay, can be written down here as minus a times of square of k times of d by 4 pi e to the power of minus k x. Okay. So, that is how rho is, and of course, there is a d term here, dielectric constant, and we will have to somehow determine what this k is in an identical manner, assuming a charge distribution and principle of electron neutrality as we did in the case of a one dimensional ionic form. So, let us assume that the charge density on the surface of the electrode is actually equal to sigma per unit area, and somehow because of the principle of electroneutrality, the electrode and solution charges should be the same as far as the magnitude of the charge goes. So, sigma therefore of the solution or the electrode can be represented as minus of the volume charge density of the solution times of dx. Okay. Because the only variation available is in the x direction, we do not consider any other direction for comparing the sigma value. So, we assume that there is a homogeneity of distribution of charges as we move along each plane along a certain value of x equal to x1, x2, x3, x4, so on up to infinity. So, if we put the value of rho here in this equation and try to solve, we actually get, and this charge density here being positive, this is of course the negative charge density, the negative sign goes away. Okay. So, we are able to see this as a to infinity times of a square of d, sorry, square of k times of d divided by 4 pi e to the power of minus kx times of dx. Okay. And this can further be expressed as a dk divided by 4 pi e to the power of minus kx. The 1 k term goes here. Okay. And therefore, a can further be expressed as 4 pi sigma divided by dk e to the power of kx positive at x equal to a, which thereby means the start of the dual layer. This value would be 4 pi sigma by dk e to the power of k a. Okay. So, that is about the expression regarding A would be, and because the term potential function xi of x is related to this A e to the power of minus qx, I am sorry, minus kx, meaning thereby that it is 4 pi sigma divided by dk e to the power of k times of a minus x, okay, where obviously the expression a, the constant, comes from this particular term here. So, therefore, we can fully write the potential xi x in this case as 4 pi sigma by dk e to the power of k minus x. In other words, at x equal to 0, x equal to, I am sorry, x equal to a, indicative of the surface of the electrode, the value of potential function, also known as the zeta potential of a surface with respect to a solution, can be represented as 4 pi sigma by dk e to the power of 0, okay, 1. So, it is 4 pi sigma by dk. In other words, the zeta potential is basically represented as 4 pi sigma delta by d. If you may remember, delta was the diffuse layer thickness, which had been earlier said to be predicted by the ion association theory as 1 by k. So, that is how the zeta potential of any surface comes into existence, and this is a very critical value which matters particularly in electrochemical machining processes, because every surface would have a characteristic zeta potential with respect to the electrolyte of interest that you are flowing in, and that zeta potential has to be somehow crossed over by the applied potential, external potential, in order to be able to furnish the electrochemical machining operation. And so, the zeta potential is absolutely important to be kept in mind to estimate things like material removal rate, etc., which happens normally during the process of electrochemical machining. So, if we look at the diffuse layer theory, where we talk about, let us say, a surface here followed by a inner solvation shell of the ions which are there in the solution, followed by, let us say, a positive ion outer plane here, and then subsequently a diffuse layer, okay, which is starting from the Helmholtz outer plane here all the way to infinity. We say that if supposing the capacitance here is capacitance of Helmholtz layer CH and here is CD, the overall capacitance which would come into existence is actually 1 by CH plus 1 by CD, or in other words C can be represented as CH CD by CH plus CD. Here if supposing CH dominates CD, okay, CH is dominating CD, let us say, so then C becomes equal to CD, and vice versa, if CD predominates CH, C becomes equal to CH. So therefore this particular model is known as the Helmholtz model, because the predominance of the diffuse layer capacitance, and this is known as the Guy-Chapman model when you talk about the capacitance modeling of a diffuse double layer with respect to any surface or any solution. So let us look at some aspects of mass transfer and electron exchange process involved therein. So in considering the electron exchange reaction at the electrodes, we are concerned essentially with the layer of solution very close to the electrode surface, as you have just seen and modeled just before, and there should be some means however available for oxidant or the reductant to reach the electrode surface. And if you look at this interface formulated with this so called double layer diffuse and Helmholtz layer, okay. So this layer has to be crossed over for any electrochemical reaction to happen and the way that they are principally done are through three processes or three steps. One of them is called migration, another is diffusion, and the third is convection. So the migration is the movement of cations or anions through a solution under the influence of an applied potential between electrodes placed in that solution, and migration automatically starts happening when the electrode just about touches the solution, and this is the reason for the double layer. And then you have of course the electrode reaction which depletes the concentration of the oxidant or the reductant at an electrode surface and produces a gradient therein, okay. So this gives rise to the movement of species from higher to lower concentration. It occurs in both charged and uncharged species. And then of course we have convection which relates to thermal or stirring effects of the solution. It can arise extraneously through vibrations, shock, and setting up of temperature gradients. So these are the three principal mechanisms in which the ions can move back and forth between the electrode and the solution and cross the double layer thus established, and that is the mechanism of mass transfer which happens mostly in even the electrochemical machining processes. So let us look at the fundamental of the ECM process here. So when a metallic body cut so just for the sake of repetition, in an ECM process the following events actually take place, okay. It starts with when a metallic body is submerged in an electrolyte, okay. The metallic atoms leave the body, becomes ions, the ions move to the body and becomes atoms. The process goes on continuously and an equilibrium is maintained, okay. The potential difference exists between a point on the surface of the metallic body and an adjacent point on the electrolyte, and this difference is known as the electrode potential, right. And the electrode potential varies depending on the electrode electrolyte combination. So this actually is nothing but the zeta potential that they are mentioning of a surface, and if two different electrodes A and B are in turn immersed together in the same electrolyte, and the potential difference is given externally between these electrodes. First of all, there will be a potential difference will automatically exist, and then you can externally give a potential difference also. There would be some kind of transport of ions from the solution into the electrodes or vice versa, and the total amount of electrode difference of potential which would thus arise is basically the potential of the electrode A minus the potential the electrode for B, okay. And that would be the net EMF which is available, which would create a condition where ions start moving, if supposing we are not giving any external field or external potential to these set of electrodes. And in the process, supposing if you have two electrodes, copper and iron, okay, as mentioned here in brine solution or solution of kitchen salt in water, and you already know that the standard electrode potentials of both these reactions where iron gets into ferrous state releasing 2 electrons is minus 0.049409 volts, and copper getting into cuprous state and releasing 2 electrons is 0.304 volts. The difference between electrode potentials, okay, of the copper and the iron electrode can be represented as the potential of the anode minus the potential of the cathode. So, it is basically potential of the copper brine solution minus the potential of this basically is the anode, okay. It is placed higher on the electroactivity series, potential of Fe with respect to the brine solution. So, therefore, this becomes equal to 0.304 plus 0.409, 0.713 volts. And the nature of electrolysis process depends on the electrolyte used, and supposing if you were to do ECM, then whatever comes out here, for example, if Fe plus 2 state comes out of this electrode here and being the cathode, okay, and this basically gets converted into immediately into FeOH2, okay. This ferrous hydroxide is not dissolvable anymore in the solution, so it precipitates down, it formulates as crystals here. So, it does not get redeposited or anything else, as a matter of fact does not get redeposited on the copper. So, this can be the tool and this can be the workpiece, and this can be a basis of electrochemical machining. So, that is what, or that is how the electrochemical machining is realized. These are the reactions, for example, the iron getting removed and the hydrogen getting split up by the 2 electrons that is released by the iron getting into H2 plus 2H minus, and the resultant FeOH2 which is non dissolvable is formulated, and this is the precipitate which can be later on removed, and it furnishes the machining operation. So, basically let us look at some of the mathematical details or estimation of the MRR or material removal rate using the Faraday's laws that we had discussed before. And as you already know that by the Faraday's laws, the amount of weight that is removed, cut, the amount of weight in grams of a material dissolved or deposited is also given by the is proportional to the ambient current, the total time duration for which this current is flown, and epsilon which is actually equal to the gram equivalent weight, okay, the gram equivalent weight of a material. And by the definition of it, the equivalent weight is 1 mole of the material, which is the weight of the 1 mole of material, which is also equal to the atomic weight per unit the valency of the material Z, okay, Z is the valency. So, we can call it A by Z, okay. And essentially the amount of charge which would have to be flown in the system is related to this quantity I into T. As you know, I already is dq by dt, the amount of the rate of change of charge or rate of flow of charge. And so this is the time integral of I, meaning thereby that this is the total charge. And when we are considering 1 mole in 1 atomic weight, the total charge that would be involved in removing this 1 mole is basically equal to 1 mole electrons, right. And this 1 mole electrons is 6.023 10 to the power of 23 times of charge of 1 electron, which is 1.6 10 to the power of 19 minus 19, would formulate the term 96,500 coulomb, which is also known as a farad. Okay. Which is also described by the term F. Okay. So this 96,500 coulomb is the unit for 1 mole charge or 1 mole electrons. So therefore, the mass rate of removal, the rate at which the mass or the weight gets dissolved or deposited, would be equal to the rate at which your flowing charge, that is the current, times of the equivalent weight that you are removing, that is A by Z, times of how many moles of current is flowing per unit time, represented by the F. So I by F is that term, right, the moles of electrons which are flowing, and so many moles, with 1 mole removing A by Z weight of a particular material at a certain rate, which is determined by this current term here, rate of flow of charge, would be the m dot, or the rate of flow of dissolution, or rate of dissolution, or rate of deposition, or rate of flow of material in fact. So basically the mass removal rate of an ECM process is therefore given by this term m dot AI by ZF. Just for the sake of repetition, A by Z is the atomic weight of 1 mole of a certain ion, and exactly how many moles per unit time is being flown is given by the quantity I by F. And so you are essentially looking at what is the mass rate which is coming out from the system because of the flowing of this particular charge. So if we assume further that the density of the anode material is rho, there can be an estimation of the volumetric removal rate. So it can be given by m dot by rho. Okay. So rate of change of mass per unit volume or per unit density, giving thereby the volume which is being emanated, or the volume rate which is being emanated. So this can be represented as AI rho z f, AI by rho z f, and the units of this could be in centimeter cube per second. For the sake of repetition again, A is the gram atomic weight of the metallic ion, I is the current in amperes which you are trying to flow, and rho is the density of the anode in gram per centimeter cube. Z is the valency of the cation of interest which is coming out or being deposited, and F is of course the amount of charge corresponding to 1 mole electrons, given by F, the quantity F of farad, 96,500 coulomb. So that is how you can sort of get an estimation of the volume rate of removal, Q dot AI by rho Z F. So this is only if predominantly one metallic system is existing, right. But however, most of the real engineering applications come when there are alloyed components, or many such metals are participative in the system, and so therefore we somehow need to tailor this mass removal or volume removal rate in a manner so that it can be applied to alloyed systems. And so today we are kind of at the end of this lecture, but then in the next lecture we will take this up and try to see that if there is an alloyed system with more than one metals participating in the process of this electrochemical removal, then what would be the overall rate based on a sort of average between all the alloys which are there in the system of different densities, different atomic weights, different valencies, so on and so forth. So we will look at that problem in the next class. Thank you.